Hi, we are group C01S01, consisting of members Elston Almeida, Edward Kang, Matteo Tullo, and myself, Helen Shelton. Today we will be showcasing our Capstone, which we affectionately call Panavista. Camera technologies have aided science and entertainment around the world. In the 21st century, cameras of varying aptitudes have enhanced surveillance and information capabilities massively, such as telescopes, microscopes, security cameras, thermal cameras, and so on. In recent years, military technology has advanced to provide pilots 360-degree video around the plane with no obstructions, but this technology has not made its way to the consumer market in an affordable manner. Consumer market products are largely entertainment-based 360-degree VR experiences. These products offer an all-around view of entertainment outlets, such as sports stadiums, via VR immersion. Our Capstone project aims to provide real-time panorama video with manageable latency using compute modules. By taking on this project, we aim to make this technology more suitable for research and other related industries, such as construction, security, and disaster response agencies, like search and rescue. Through this video, we will introduce to you our technical modules. Module 1, the drone, Module 2, the headset, Module 3, the head tracking, and Module 4, the video processing feed.
For my module, I focused on building the drone as well as helping the headset enable firmware. For the headset, there exists two microcontrollers on board that I programmed firmware for. The first one being the STM32. It talks to the USB-C PD chip by configuring a one-time programming of its firmware. Additionally, the STM32 configures the registers of the battery charging chip. The second microcontroller that we have on board is a Wi-Fi microcontroller, the ESP32. The main goal of this is to connect to the host PC via Wi-Fi and set up a TCP connection. This is the drone that we built. For the parts, I picked out a open source flight controller running firmware called Betaflight. I also had to take into consideration what motors to pick, as well as the current limits for the ESC and the current limits for the battery. Efficiency was also something I had to calculate based on the power of the motors running at idle, as well as the payload weight that we needed to carry.
In my module, I was working on the headset, a way to integrate the IMUs and also be able to enable wireless communication between the headset and the base station. The idea of building a PCB was assigned to me. We enabled being able to connect up to a LiPo battery or lithium-ion battery, also being able to provide battery charging. Additionally, peripheral devices, or any such things that want to be powered over USB-C. All of this would be then on one board, connect down to the base station, where it would send all the IMU data, creating the schematic, and then doing the layout. It was done inside Altium Designer, and was then bound by JLC PCB. When the board was back from JLC PCB, people who were writing the firmware were aware of exactly what ICs were on the board and how exactly the board was expected to work. Soon thereafter, during the bring-up process of the board, everything was basically built inside IEEE using their resources such as the reflow oven, their hot air station, their soldering irons, and through that process I was able to then ensure that the board was fully functional and working as per intended.
Module 3 is basically all about how do we get the data that we're going to get from the IMUs that are on the user's head into Unity so that we can properly track it in the VR space. MQTT is a simple framework between the IMU headset and the base computer that we'll be doing our Unity and our data processing on, and using TCP protocol to communicate between the programs on that base computer. Positional data, like quaternions, we decided to directly feed that data using MQTT into Unity. We've set up a script where we apply a simple moving average filter to try to smooth out any noise that are coming in from the IMUs, and just use multiple IMUs to try to fix any drift that happens naturally. The mechanical design of the headset was done in AutoCAD Inventor. The approach was we got just a phone VR headset that can put any phone into it so that you can view it, and we designed components in Autodesk Inventor to attach onto the straps of the headset, attach our dongles and a mounting board for our PCB and our battery.
In my module, I cover the video processing unit, which is done through the video game engine Unity on the base station. To begin, we first established the ability to receive one video camera data stream in Unity from the Raspberry Pi, which is hosting a TCP server over a Wi-Fi connection from the drone, onto the base station using the open source video pipeline GStreamer. We then scaled that to 4 camera streams to enable a more immersive view. Unity receives the stream over the air from the drone using a TCP socket connection in .NET, which is written in C# and bound to Unity object. Once the data is received, the pixels are converted from the YUV color space to the RGB color space that Unity understands. YUV uses 1/6 of the data of RGB, thus making it faster and more efficient to stream over the network. Then the pixels are mapped to what is known as a texture in Unity and projected onto a material, which in our case is a 3D plane called a quad. We implemented a custom circular buffer algorithm to deal with the continuous stream of data coming in from the cameras. And thus ends my portion of the module.
Here is our Raspberry Pi connected to our 2 cameras, connected to a router via Ethernet. Here we enable the GStreamer commands on the Raspberry Pi. 1 camera, 2 cameras, and we can see that the cameras have turned on. Here is our willing subject. We can see a phone connected via HDMI to our base station. Our base station is running Unity. Panavista is in the back, and our IMUs are up on top. Turning on the Panavista. 2 green lights ensure that it is connected to the MQTT broker. Play. You can see it in real time with Helen holding the 2 cameras. Try waving, Helen.
I would if I had an extra hand.
Yes. Drop 1 and wave.
Gotcha.
We can see this in real time. Please move your head around. Perfect.